Okay, now we're going to do the window problem, our free convection on the inside of a window. So here is our window. No, pen. Let's try green. There we go. Look, here's our window. Okay, and the thickness of our window is 0.004 meters, 4 millimeters. Now on this side we're going to have free convection because it's inside. On this side we don't know. So here on the outside we're not going to assume free convection. So we're going to assume it with free convection on the inside, and we're not going to assume free convection on the outside. So I know T surface inside is 33 degrees C, and I know T infinity on the inside is 21 degrees C. So here I have my window, and its height is 2 meters. Okay, so we're going to have some boundary layer that forms, and we're going to have free convection, this is the moving fluid, on the inside surface of the wall. So how do we calculate this H here, H inside? Alright, well, step one is figure out a film temperature. Now, thankfully here, we know T surface, 33. We know T infinity, 21 over 2. Yes, the problem's been gamed to give us a T film of 27 degrees C, or 300 Kelvin. So, which equals 300 Kelvin. I'm going to look up properties. I need my kinematic viscosity, 15.89 times 10 to the minus 6 meters squared per second. I need the Prandtl number, which is 0.707. And I need the conductivity of the fluid, which is 0.0263 watts per meter Kelvin. And I need my volumetric thermal expansion coefficient, beta, but I remember that it's 1 over T film, again, because I'm dealing with an ideal gas, air. If it's something other than an ideal gas, make sure you look it up in the tables. Okay, how to calculate a Rayleigh number? Rayleigh number is G beta Ts minus T infinity L cubed, Prandtl number, over the kinematic viscosity squared. Well, now the question is L. So for a vertical plate, the characteristic length is the height of the plate. So in this case, L will be 2 meters. So L equals 2 meters. Okay, everything else is known. My Rayleigh number comes out to 8.79 times 10 to the 9th. Now in your book there are a couple of correlations. The first correlation is good for a Rayleigh number greater than 10 to the 9th, and that's that the Nusselt number equals 0.1 Rayleigh number to the 1/3. If you use that correlation, you get 206.4. There's another correlation which is good over a large range of Rayleigh numbers, and it goes like this: 0.825 plus 0.387 Rayleigh number to the 1/6 divided by 1 plus 0.492 divided by the Prandtl number to the 9/16, all of that in the denominator raised to the 8/27, and then all of that squared. What a mess. 242.1. Alright, now you'll notice both equations are valid, okay, but they did not give us identical answers. Alright, so we're left with picking one. I'm going to pick this one right here, and my value for H is going to be the Nusselt number times the conductivity of the fluid divided by L, same L, and H is going to come out to be 2.71 watts per meter squared Kelvin. Alright, part B says calculate the rate of heat transfer through the wall. Well, if here's my wall, and I know this temperature here, T surface inside, and I know this temperature here, T infinity, and I know H, right? Then I can use just a simple, kind of made a mess here, resistor circuit, or just the equation for convection. Q equals H inside area, T surface inside minus T infinity inside. That gets me the Q going in that direction. Okay? So Q comes out to be 65.04 watts. Okay. The next part of the problem says calculate the convection heat transfer coefficient on the outside. Alright, well here's my resistor network. Let's just draw the resistor network. T infinity inside. Here's T surface inside, R conduction. T surface outside, R convection. T infinity outside. Now I know this is 33 degrees C. We've already figured out Q is 65.04 watts. So I can figure out this temperature or all at once. I'm going to find T surface outside first. So R conduction is L over Ka, where that's the thickness of the glass, 0.04 meters, 4 millimeters. Conductivity of glass, you can look it up in your book, is 1.4 watts per meter Kelvin. And the area is 2 meters squared, right? Because our window was 1 meter by, area was 1 meter by 2 meters. Okay? So my conduction resistance comes out to be 0.0014 Kelvin per watt. So Q is T surface inside minus T surface outside. Actually, the other way around. Surface outside minus T surface T surface inside divided by R conduction. Solving for T surface outside, I get 33.09 degrees C, so not much of a drop across the glass. And then finally I can say Q, same Q, equals H outside A, T infinity outside minus T surface outside. Or you could do this with a resistor, it doesn't matter. So H outside equals Q over the area, T surface outside, T infinity outside. Fine. Let's erase. I need to find a way to make this get easier to get to the eraser. Whoa, what happened there? T, what the heck? And T infinity outside minus T surface outside, and that gives you an H of 17.0 watts per meter squared Kelvin.